surprising, but we're actually right on schedule. So our last presenter this evening is Ian, and he's been the presenter here at the QASIG before. He's also a former core dev employee, and when his project ended here, he ended up going down to Blue Origin, and now he's building rockets, so we have a real rocket scientist. So he's going to talk about, let me see if I get this right, even though it might not be your exact, so hardware-in-loop testing, is that what you're still going to stick with?
That is what I'm going to talk about.
All right, yeah, well, welcome back.
Thank you. Okay, first I get to do the technical stuff here. Find my snapshot. How much do I hate Windows? Let's see.
Alt-tab.
That makes sense.
So three for three for needing technical help.
How many I can give them to it?
It's only the first PowerPoint I've done in a decade.
It's a hardware thing. It's not
PowerPoint actually.
I have it. Well, good evening, everyone. So I'm talking about hardware and loop evaluation this evening because usually when I talk about it, people look at me funny. They kind of stare at me and say, what is that? And that includes people who apply for jobs at Blue Origin. It is a little specialized. It's probably not something that most of you have encountered unless you worked in something like aerospace. But it is kind of an interesting take on testing, and it I think gives some context into some of the assumptions we get to make with modern application platforms. So, you know, most people work with a common platform. It's a PC, it's a Mac, it's Android, it's whatever iPhone they're putting out this week. But what you get to do is you get to write code, not worrying about the platform really. If you have problems with the platform, that's somebody else's problem. So the way that you're testing is you're either going in through the product hardware, you're using the user interface that's available to the user, or talk about automation, you're going in through API hooks, you're going in through some other way of being able to directly interact with the software. And the software is what you're testing. You're not testing the hardware. The hardware had better work or Apple is in trouble. Now, some of us have it a little differently. Now, I picked these two pictures because my two experiences with hardware and loop testing have been at Boeing, where I taught Boeing engineers how to use their hardware and loop software, how to use their simulation system. And now at Blue Origin, where I'm a hardware software simulation engineer in our hardware lab, and I work with slightly larger things, vehicles that actually fly themselves. So it's kind of important that we make sure it works, especially when we start putting people on top of them. Software quality, very important when 6 lives are on the line. I don't want to be mine. So, this is how you could test things. And in fact, this is our history. We would build rockets, we would say, well, let's see how it works. And hopefully, everything goes fine. Everybody probably knows about the Ariane 5 disaster. Yeah. So, you know, there were things that could have been done, weren't done, that would have caught this problem early on, and hardware and loop testing would certainly have been one of them. The problem that we saw in Ariane 5 is actually a class of problem that I have seen in our Hill lab. Not because people aren't paying attention, not because people are sloppy, but because these are complex systems, and we need to understand them fully. So, in distinction from what I was talking about earlier when we were developing on a tablet, you blow things up to get you talked about, especially if there are people involved. So I want to talk about just a classical control system. So what we have is we have sensors that tell us about the world. You know, what is the world outside me? What is the world I'm doing? You know, how fast do I think I'm going? How much thrust am I putting out? And this goes into my control hardware, is interpreted by my control software, which then goes out to actuators. So I can now modify my world. I modify my fin positions, I can modify my thrust, my pressures, and so forth. So classic control system. So what do we do in a hill lab? Well, what we do is we simulate at least part of the sensor actuator environment. It's a very interesting question, just how much. And these two examples will give you different perspectives on how different vendors have done this. But the basic idea is, all right, I've got this simulation that says, I know how fast you are going. I know what your pressure is because I'm simulating a sensor in the engine. And you tell me what I should do with the actuators, and I will move numbers in my simulation that then changes the simulation world and now changes my sensor input back into my control systems. It's really as simple as that. How do you test in this environment? You can push information into either the simulation side, actually typically the simulation side, or in certain cases into your control software side, especially for things like fault injection. So fundamentally, a very simple problem. So again, talking about these two different examples, Boeing built a simulation package called PSIM. It was really amazing when I worked with it. It had been around for 25 years on about 5 different platforms, and it did not substantially change across them. It allowed them to build the entire aircraft and decide which parts of it they wanted to actually connect into the simulation. So this was a pluggable simulation, and you could have as little or as much of the actual hardware as you wanted. This is used for instance, the motion cabs that they use to train new pilots on planes that don't exist yet, because they can hook it up to all of these complex actuators in the motion cab that understand the geometry of what's going on with the aircraft in simulation. The data was shared through shared memory, which simplified this problem of figuring out how to hook things in. They did it with single board computers. And they can also drive the simulation through stored data. So this was used all throughout a vehicle's lifetime, including in accident investigation. They would take flight data recorder information, play it through the simulation, and discover what had happened. Now, what we do is hardware and simulation. What's very important to us is understanding that not only that we have the software right, but that we have the hardware put together right. Again, very complex systems with a number of computers spread throughout the vehicle. So we need to worry about things like network latency and packet collision. And you would not believe some of the interesting, very little things that we find that can create marginal conditions. We get different test results on different test runs. This is not a good thing. We need to understand this. All the data is shared through telemetry, because what we're trying to do is recreate the vehicle environment as faithfully as possible. So the flight side of this, the control software, the control hardware, is all authentic, which means these are $50,000 computers. But we really test with what we fly, because that's what's going to go into space. That's what we need to understand. So we use not only the hardware and software, but also the communication fabric that we use in the actual vehicle. So here's a picture of how you might use PSIM. And I actually saw this used where the instrument under test was, I think, an altimeter. And so you go through a single board computer that was running VxWorks. It connected to the hardware over Ethernet. It connected over any of like a dozen different common aviation protocols to the system under test. You logged your data. And Boeing tried to use this on the 787 for integration testing. What they wanted to do was have everybody on the field across the world do component testing, and then they just do integration testing. Didn't work quite that way. It was a great plan. Execution is everything. So here's an example of what I'm doing. Down in blue, got my simulation over here. That's my engine model, my sensor model, my actuator models, and my world model that includes all of this very complex aerodynamics that some really, really smart people with multiple PhDs figure out. Scary. So I've got telemetry coming down from both the flight side, and this is very authentic, and the plant side, the simulation side. And when I'm done with whatever test I'm doing, I compare these two. That's where my data comes from. What did the vehicle really do, and in what environment was it doing it? We try to be as non-obtrusive as possible in the flight side. We tend to muck around a little over here. But this needs to be really what we put on the rocket. So this is kind of a co-evolution process as distinct from most software development in the commercial or consumer world, because it's very typical that we are learning about the hardware as we're testing the software in the HardwareInLoop environment. So it says it does this. Well, it doesn't do that. There was one recent incident where it didn't support a particular network protocol because we needed to use a different switch because we couldn't fit the other one in the vehicle. And we would never have discovered that if we hadn't actually wired the thing together and tried it. Sounds pretty straightforward, right? And yet, think about the history of aviation, the history of aerospace, and some of the really spectacular accidents, fortunately most not involving people, that we've seen with this older model of, well, let's build one and see. By the way, let's build one and see when they cost $10 million or $20 million. It's expensive, it adds up really fast. So HardwareInLoop, even though it itself is very expensive, I mentioned $50,000 flight computers, is a lot cheaper than losing a rocket. And we landed the same rocket 5 times.
Wow.